Yeah, exactly. So I'm very pleased to introduce our first speaker of the last morning session, Anna Schilling, giving us her third lecture on diagram algebras, insertion algorithms, and plethism.
Yeah, thank you very much, Travis, for the introduction, and again to the organizers for putting on this conference, and happy birthday again to Masato Okado. Yeah, so today I want to talk about some joint work with Rosa Orellana, Franco Saliola, and Mike Zabrocki that has appeared in various papers. And so I want to start quite simple. Namely, what I first want to do is introduce the RSK algorithm. And the reason is because we want to explore some variants of the RSK algorithm. Namely, usually when you use the RSK algorithm, you insert integers. And what we want to do is eventually insert multisets instead of integers. And the RSK algorithm is sort of a combinatorial way to understand the double centralizer theorem when you look at certain representations, GLN representations. So what does a double centralizer theorem say in general? Well, if you have some representation V and you have two algebras, let's say A and B acting on V, then if these commute with each other, so let's say A acts on the left and then you have a commuting action of B on the right, then you have this decomposition of V into irreducibles, tensor products of irreducibles, where A only acts on the U lambda and B only acts on the VW, W lambda, sorry. So what we want to do is we want to apply that to what are called partition algebras. So the insertion algorithm that I'm going to describe takes partition algebras and spits out a standard tableau and a multiset value tableau. And it turns out, and this is sort of like the amazing part, is that this is in fact well behaved with respect to subalgebras. So the partition algebra has a lot of important subalgebras. So for example, the Temperley-Lie algebra, and this insertion is well behaved with respect to that. And then just as for the usual RSK algorithm, the dimensions of the irreducibles actually turn out to be the number of tableaux. And then at the very end of the talk, what I want to do is I want to look at some other subalgebra of the partition algebra, which is called the uniform block permutation algebra, or also sometimes called the party algebra. And then we will see that there's a relation to plethism. And then I will circle back to sort of my first talk where we talked a lot about crystal bases. And I will pose an open question related to this. So that's sort of the plan of the talk. So let's start with just a review of the RSK algorithm and the relation to representation theory. So the first instance of the RSK algorithm, or also called Robinson-Schoenstatt-Knuth correspondence, was given by Robinson in 1938. And in this setting, you take a permutation in Sn, so just a permutation on n letters, and the permutations in Sn turn out to be in bijection with pairs of standard Young tableaux. So by SYT, I denote standard Young tableau. So that's the first incarnation of this Robinson-Schoenstatt-Knuth correspondence. Then what you can do is you can upgrade that. Instead of looking at permutations, you can look at words of length n, but now in some alphabet k, where k is given by the letters from 1, 2 up to k. Okay, so if you upgrade the Robinson bijection to this setting, then you will get the correspondence with pairs of where the first one is a semi-standard Young tableau, so SSYT for me denotes semi-standard, and then the second tableau is still a standard Young tableau. And then you can generalize this even further by looking at generalized permutations, and I will define what I mean by that in a moment, over n and k of length L, and then you get that both tableaux are actually semi-standard Young tableau. So in the previous settings, one of the tableau was a standard Young tableau. So let me begin by telling you what I mean by a generalized permutation. So in this setting, you have two ordered alphabets, A and B. So for example, take the letters from 1 up to N and the letters from 1 up to K. And they are ordered, right? Because 1 is smaller than 2 is smaller than, and so on, is smaller than N. Okay, and then a generalized permutation is a two-line array where we take letters from the first alphabet, so from A in the top row, and letters from the second alphabet in the bottom row. And we want that the top row is weakly increasing. So since A is an ordered alphabet, we have an order, so we know what weakly increasing means. And then we have a condition on the letters B as well. Namely, we want that the letters B are weakly increasing whenever the letters in the top row are equal. But if they're not equal, then there's no relation between the letters, the BI and BI plus 1. So here's an example. Here I'm looking at a generalized permutation where the alphabet A is the numbers from 1 up to 6, and the alphabet B is the numbers from 1 up to 5. So you can see that the top row is weakly increasing, right? I have 1, 1, 1, 2, 2, 3, 3, 3, 3, and so on. And the bottom row contains only the numbers from 1 up to 5, and you can see that whenever the top row is equal, the numbers there are equal, then the bottom row is weakly increasing. So this is a generalized permutation. So now I want to briefly review how to do row insertion, because the RSK algorithm relies on row insertion. So suppose you already have a semi-standard Young tableau of a given shape, and here I use French notation for semi-standard Young tableau. So I have a shape, and I want that the letters in each row are weakly increasing and letters in each column are strictly increasing. So suppose I want to insert the number 2, then I look at my bottom row and I look at the smallest number that's strictly greater than 2. So the number that I want to insert, in this case, it's a 3. The 2 will bump the 3, and then the 3 will then be inserted in the top row. So the 3 will look for the smallest number that's bigger than 3. So that's a 4. Then the 4 will be inserted in the next row, and so on and so on. So at the end of the day, a new letter is actually sort of appended to your shape or to your tableau. So in this case, we have this new box up here where the 7 is. And then how does the RSK correspondence work? Well, you take a generalized permutation, and one by one, you row insert the letters B1 up to BL. And you also record wherever you add the new letter, when you do this insertion, you keep track of that by a recording tableau where you insert the letters AI. So from the top row. And then Knuth proved that there is indeed a bijection between generalized permutations from A to B and pairs of semi-standard Young tableau, P and Q, where the shape of the two tableaus equal. P is a semi-standard Young tableau with entries in B, and Q is a semi-standard Young tableau with entries in A. So that's a review of the RSK algorithm with generalized permutations. Now I briefly want to remind you also how this is related to representation theory, because that's what we want to apply it to in a more general setting. So let me do that in terms of the Schoenstatt correspondence, where we go from words of length n in the alphabet K to a pair of a semi-standard Young tableau and a standard Young tableau. So associated to this, because we have a bijection as an enumerative result, right? So if we count the number of elements on the left side, the number of words of length n in this alphabet, well, they are k to the n such words. And then because this is a bijection, we immediately get that this is equal to the sum of the number of semi-standard Young tableau of shape lambda times semi-standard Young tableau, standard Young tableau of shape lambda, and then we sum over all lambda partitions of n. So that gives us an enumerative result. But you can also interpret this in terms of representation theory, namely, suppose V is C to the K. So we know that GLK acts on that. And let's now take an n-fold product of this. Then we have like the diagonal action of GLK on this tensor product. But you can also act with Sn by permuting the tensor factors. And these are two commuting actions. And therefore, this V to the n actually decomposes into, well, a simple left GLK module tensored with a simple right Sn module, and then you sum over all possible lambda. So that's a representation theoretic interpretation corresponding to this RSK algorithm. Okay, so what we want to do now is we want to take these classical results and apply them to diagram algebras. So what we are after is we want to encode partition diagrams, and I will define for you what I mean by a partition diagram as certain generalized permutations that are filled with multisets. And then we are going to use the RSK algorithm to produce, again, two pairs of tableaux that have the same shape. And as I mentioned before, this insertion algorithm or this correspondence is well behaved with respect to taking subalgebra. So that's kind of the surprising aspect. And it also matches the representation theory of Halvorsen and Jacobsen for these partition algebras. And it also gives a new map from standard multiset tableau to Bratelli diagrams. I won't actually describe that in this talk, but I thought I would mention it anyway, which is different from a map that was given by Bankert and Halvorsen. Okay, so now let's get started. Let me first tell you what I mean by a partition diagram. So a partition, what we want to do is now we want to partition sort of the union of two alphabets, the alphabet from 1 up to K, and another alphabet from 1 bar to K bar. So we have two alphabets of the same length, but we denote the letters either with unbarred letters and with barred letters. So here's an example. In this example, for me, K is equal to 8, right? So we have an alphabet 1, 2, 3 up to 8, and then also 1 bar, 2 bar up to 8 bar. And then this pi that I've written here is a partition of the union of those two alphabets, right? So what is a partition? That's just, these are subsets of the full set that are non-empty, and the intersection of any two such sets should be empty as well. So there should be no overlap, right? So you can see that every letter in K or 8 union 8 bar is indeed in this partition. And we are going to represent this partition by a diagram where we write the unbarred letters in the top and the barred letters at the bottom. And then we are going to connect all the letters that are in one of the blocks of the partition. So for example, 1, 2, 4, 2 bar, 5 bar are together in one block. So in my partition diagram, those letters are connected. And it doesn't really matter for me, for this talk, it doesn't matter how we connect them. It just matters that those form a connected component. And you can see like the 1 bar is a singleton. So the 1 bar in our partition diagram is not connected to anything. Okay, and then the partition algebra is spanned by these partitions of the union of the set 1 up to k and 1 bar up to k bar. We are going to call a block propagating if it contains vertices from both the unbarred and the barred letters. And yeah, here's an example. So the first block, right, the 1, 2, 4, 2 bar, 5 bar is propagating because it contains unbarred letters, 1, 2, 4, and it also contains barred letters, the 2 bar and 5 bar. And if they are not propagating, well, then we call the block non-propagating. So for example, the block 3 is non-propagating because it only contains unbarred letters, and the block 1 bar is also non-propagating because it only contains barred letters. So now I'm going to tell you how we are going to use the RSK algorithm for these partitions. So suppose we are given a partition of this union of alphabets, and I'm going to call the blocks pi 1, pi 2 up to pi r. For the RSK algorithm, remember we need an ordering. So the ordering that I'm going to use is you look at the maximum of every set, and you're going to compare the maximal elements. So that's also called the last letter order. And it turns out we actually only need to compare either the barred or unbarred letters. So that's why I don't need to put an ordering on the barred and unbarred letters, only separately. So now I'm going to treat the propagating and non-propagating blocks separately. So suppose pi j1, pi j2 up to pi jp are the propagating blocks. Then I'm going to denote by pi upper plus just the letters in that block that are unbarred. Okay, so that's what is denoted here. So the pi plus just denotes the unbarred letters, and then the pi minus denotes the barred letters in a given block. And then I'm going to call sigma I1 up to sigma IA the non-propagating blocks just in the alphabet K, and tau I1 up to tau IB the non-propagating blocks in K bar. Okay, so then what we are going to do is we are going to form a generalized permutation by putting the pi pluses. So remember, we are taking the blocks, and we are only looking at the unbarred letters in those blocks. So that's what the pi upper pluses mean. We put those in the top row, and we are ordering them by this last letter order. So they are ordered, and then in the bottom row we are putting the pi minuses, so the barred letters of the corresponding blocks. Okay, and then we are going to perform RSK on that. And because we have an ordering on those blocks, we can just use the usual RSK algorithm, right? But instead of integers. We are just using now these blocks. And then we are going to define T to be the insertion tableau P by adjoining a bottom row to our tableau. So remember, in the partition algebra, there's also this parameter n. So we are going to, if n is very large, then we are just going to adjoin a very long row. And then we are going to put these non-propagating elements in the bottom row and leave the other elements empty, the other blocks empty. And then similarly, S will be the recording tableau, and then we are going to adjoin the unbarred letters. So here's an example of how you would do that. Here is a partition where k is equal to 9, and my n I'm going to take 18. Then you can see that here I've taken the p pluses in the top row, and I've ordered them such that they are increasing if you compare the largest letters in each of the blocks. And then, so 2, 3, 4 was in this particular block. So therefore, in the bottom row, we have 4 bar, 5 bar, and so on. And also note that the non-propagating blocks are not actually listed here. So then we perform the usual RSK. And if you do that, you get these two tableaux of the same shape. And then the algorithm, well, is such that you add another very long row. So that the size is determined by the 18. And then we are going to insert the letters for the non-propagating blocks. Okay, so that's the algorithm. And so the consequences that we can get from this are the following. So if we denote by SMT k lambda, the set of standard multiset tableau over the alphabet k, then using this particular algorithm that I've just described, we can show that there exists a bijection between set partitions of this union of alphabets and unions of tuple of these tableaux, where one of the tableaus is in the barred alphabet and the other tableau is in the unbarred alphabet. And the nice consequence is, well, because we have a bijection, we get an enumerative result because the number of set partitions is given by the Bell number. So this is this B2K. And then because we have a bijection, this is equal to the sum of the squares of the numbers of these set of semi-standard multiset tableau. So we get an enumerative result. So I mentioned before that the nice thing, I mean, even though it doesn't look very spectacular, but the nice thing about this insertion is that it's well behaved with respect to subalgebra. So that's really where the power of this lies. So instead of looking at all possible partition diagrams, you can look at certain subclasses of partition of these set partitions. So for example, permutations are a subclass of these where you always connect one element from the top with one element from the bottom, right? So that would give you a permutation. You can also look at perfect matchings and so on and so on. So I've listed like a bunch of subclasses of these set partitions that come up a lot in the literature. Okay, and if you look at these subclasses, then they actually correspond to certain subalgebras of the partition algebras. So for example, the Temperley-Lee algebra would correspond to planar perfect matchings. And then I've also listed the dimensions of these algebras here, right? So we have already seen that for the partition algebra, it's a Bell number, and for the temporally leap algebra, it would be the Catalan numbers. So under this bijection that we had, so from the diagrams, partition diagrams, to the tuple of a tableau, we want to see whether the properties, so for example, being a permutation or being planar and so on, whether that carries over. And even though the details of the slide are not important, but what is important is that you can actually define what matching means on the other side, so on the tableau side, and you can also define what non-crossing means on the tableau side, and you can also define what planar means on the tableau side. So you can actually write down explicitly what those conditions are. So I've done that here, but as I said, the details are actually not important for this talk. And then it turns out that, yeah, under this bijection, the tableau that you get can be characterized explicitly. And here I have listed for you how you can actually characterize the tableau explicitly. So the consequence of this is that we get certain analogs of the results that you get for RSK. So for example, if you take one of those subalgebras AK and you look at certain irreducible representations for these, then you can deduce that the dimension of these irreducibles is precisely the number of these multi-set tableau that I defined before, where this sub AK just refers to like which subalgebra you are using. And I've, on the previous slide, I have given you explicitly how those are characterized. And then similarly, right, for RSK, if you look at Sn, well, how many elements are there in Sn and factorial, and you can write n factorial as the sum of a product of the size, the number of standard Young tableau, the square of the number of standard Young tableau, and the analog of that result in terms of these partition algebras are that we can write down the dimension of these subalgebras again as the square of the numbers of these tableaux, and then we sum over all possible partitions of n. So we get the analog of the analog of the usual statements for Sn. Okay, so next, what I want to do is I want to investigate this a little bit further. So one thing that we have looked at are these commuting actions. So what I now want to do is we've seen that GLN acts diagonally on V to the K, right? So if V is a representation for GLN, so it acts diagonally, but Sn is a subalgebra of GLN, so we can restrict this diagonal action to Sn, right? Where sigma, so a permutation in Sn, would just act while diagonally on each factor. If we do that, the question is, well, what commutes with this action? So when we took the full GLN, the commuting action was Sk, right? Because we are permuting the factors in V to the K. But if we restrict GLN to Sn, the question is, what is the commuting action? And it turns out that this is precisely this partition algebra that we've just discussed. And this result was given by Martin and Jones in the 1990s. And so what we can deduce from that is that, well, both SK and GLN are centralizer pairs, but the partition algebra and SN also form a centralizer pair. Okay, so here are just some pictures of Martin and Jones. So now what I want to do is I want to put those two results together in what are called seesaw pairs. And a very good exposition on seesaw pairs is given in this book by Goodman and Wallach. Okay, so what they state in their book is the following. So suppose you have two algebras A and B, and A is a subalgebra of B. Then what you can do is you can look at, well, an irreducible representation of B, and you can look at the restriction of this when you restrict to the subalgebra A. If you do that, then your irreducible representation will decompose. So it will decompose into irreducibles for the subalgebra A. And each irreducible will come with a certain multiplicity, which I here denote by C lambda mu. Okay. But now suppose that you have the setup where the algebra B and C actually form a centralizer pair, and then the algebra A and D also forms a centralizer pair. So you sort of have this seesaw. And then what is known is that the simple modules for B and C, they are actually indexed by the same indexing set. And similarly, the simple modules for A and D also have the same indexing set. And furthermore, if you now actually look at irreducible representations for the algebra D, and you now restrict from D to C, then, well, as before, right, this will decompose into irreducibles for the subalgebra C, but it turns out that these multiplicities are actually the same as the multiplicities here, except that you are now actually summing over the other index. So now what I want to do is I want to apply this to the setting that we looked at before, right? So we saw that Sn is a subalgebra of GLN. It also turns out that Sk is a subalgebra of Pk, right? Because remember, these partition diagrams, they do contain permutations. If I just connect exactly one element from the top row with one element from the bottom row. So this is indeed a subalgebra. And well, we saw that GLN and Sk form a centralizer pair. And we also know that Pk and Sn by Martin and Jones, we know that they form a centralizer pair. So therefore, by these results on seesaw pairs, we know that the restriction numbers, when you restrict from GLN to Sn, you can actually understand these restriction numbers also by looking at the restriction from Pk to Sk. Okay, so to understand these numbers, what we are now going to do is we are going to look at representations of Pk and Sk. What we want to understand is that restriction. Okay, and the way that we are going to do that is by looking at another subalgebra, which is called the uniform block permutation algebra. So this will be a subalgebra of Pk. And it turns out that when you restrict Pk to Uk, you can understand the coefficients by some generalized Littlewood-Richardson coefficients. But when you restrict UK to SK, those coefficients actually turn out to be special cases of plethism, which I will discuss more further along in the talk. And it turns out that understanding plethism coefficients is actually a very hard problem. But at least looking at the problem in this way, by putting in the subalgebra, you sort of, at least reduce the problem to another problem. Okay, so what we want to do next is we want to understand the representation theory for this uniform block permutation algebra. And in particular, we want to find some combinatorial model for the representation theory. And it turns out that you can do that by actually looking at representation theory of certain semigroups, and a lot of the representation theory is already known, but you can apply it to the setting. So that's what I want to do next. So first I need to explain to you what the uniform block permutation algebra is. And this is related to the party algebra, which was introduced by Tanabe and Kosuda. And they are centralizer algebras for complex reflection groups. And here's now the definition. So the reason why we call them uniform block permutations is because we are now going to require that the number of barred letters and the number of unbarred letters in every block is the same. So that's this condition that I'm giving here. So the intersection of block I, so DI, with the unbarred alphabet is the same as the number of the size of the blocks, or the size of the number of barred letters in the same block. So that's why we call it uniform. And so by UK as a set, this will just be the number of, the set of partitions such that D is uniform. So here's an example, right? So here my K is again 9. And this I claim is a uniform block permutation, because you can see that every block indeed has the same number of barred and unbarred letters. So the first block has 1 unbarred and barred letter. The third block has 2 unbarred and barred letters, and so on. So when you have a uniform block permutation, you can actually think of it as a size-preserving bijection, right? In the following sense. So if we put on the top row the sort of blocks where we put only the unbarred letters, and then we put in the bottom row the blocks, but the parts of the blocks with only the barred letters, then you can see that you can view this as a generalized permutation where we are now mapping 2 to 4, 5 to 7, 1, 3 to 1, 2, and so on. And it's size preserving precisely because we are assuming that the number of barred and unbarred letters is the same. Okay, so yeah, that's why we call these uniform block permutations, because we can view them as permutations. Okay, so you can, again, as before, you can describe the blocks, or describe the partition in terms of a diagram by connecting the letters that are in a given block. So 1, 3, 1 bar, 2 bar are in the same block, and that's why we have those letters in a connected component. So these actually, you can take products of such elements by just stacking them on top of each other. So here is, for example, a particular uniform block permutation. D prime is a different one. And we can take the product by stacking them on top of each other and then just looking at the connected components that you get at the end of the day. So here's an example of that. To understand the representation theory of the uniform block permutation algebra, we need to understand the idempotents. And the idempotents are given as follows. So they are indexed by partitions, but now just of the alphabet K, not of K union K bar. And we are going to define them by just putting so if you have pi, which is given in terms of blocks of unbarred letters, and then you take the same blocks for the barred letters. So that's what I mean by A union A bar. Then I'm claiming that this is actually an idempotent. So here's an example. So now here I'm writing my my partition by just sort of putting vertical lines. So when I write 2 vertical line 7, vertical line 1, 4, and so on, I just mean that 2 is 2 by itself is a block, 7 is a block, 1, 4 is a block, 3, 6 is a block, and 5, 8, 9 is a block. Okay, so we can write those as diagrams. And so the way I've defined it is, so 1, 4 is in a block, but then I take sort of the same block also for the barred letters. So that's why at the bottom I also have 1, 4 in a block, and I connect all of those. And you can see that this is an idempotent because if I stack E on top of itself, right, the connected components don't change. So that's why E squared is equal to E. So they indeed form idempotents. And we showed that in fact, this gives you a complete set of idempotents in this uniform block permutation algebra. So it turns out that when you look at the representation theory for monoids, then the idempotents actually play a central role. So that's why we needed to classify the idempotents. And it turns out that the maximal subgroups inside a monoid are precisely indexed by idempotents. So by GE, I'm going to define the unique largest subgroup of a finite monoid M containing this idempotent E. And it turns out, again, without giving you all the details, that the maximal subgroups for this uniform block permutation algebra indexed by the idempotent E pi is given precisely by the partitions such that the top and the bottom, so if you only look at the connected components in the top and the connected components in the bottom, they should be partitioned in the same way. So here's an example. If pi is given by this partition of the alphabet from 1 up to 6, then my claim is that the maximal subgroup indexed by this particular idempotent is given as follows. So 1 and 2, right, both have to be blocks, separate blocks in the top and the bottom, but you can permute the blocks of the same size. So for example, here 1 goes to 1, 2 goes to 2, but you can also permute and set 1 to 2 and 2 to 1. And similarly, the blocks of size 2, so the blocks themselves have to be the same on the top and the bottom. And then for this maximal subgroup, you just permute the blocks on the top and the bottom, right? So here, this particular block is mapped to itself, but for this particular case, they are swapped. And it turns out that, well, if the type of my partition is the following, the type of the partition of the set is given by the following partition of an integer, then the maximal subgroup is actually a direct product of symmetric groups. So by this, I mean you have A1 blocks of size 1, A2 blocks of size 2, and K blocks of size K, right? So the A1 up to AK just tell you how many blocks of a given size you have. And then it turns out that the maximal subgroups is just the direct product of these symmetric groups. So as I mentioned before, in semigroup theory, the representation theory of certain monoids is already well studied. So for example, if you read this book by Steinberg on representation theory of finite monoids, then you will see that the simple modules of such a monoid is indexed as follows. So the indexing set will now be tuples of partitions. So now partitions of an integer, where these are partitions such that if you do this weighted sum of the sizes of the partitions, you get K. So here is an example. If I want to know what is the indexing set of my simple modules when K is 3, well, then in the first entry, you can put all possible partitions of 3. So 3, 2, 1, 1, 1, 1. But you can also have a non-empty partition, let's say in the second slot. So for example, here I put the partition 1 in the second slot, but that's weighted with 2. Since we want everything to add up to 3, the first partition actually has to have size 1, and that's why here we have a partition of size 1. Or you can put just a partition of size 1 in the third slot that's weighted by a 3, so therefore the other two partitions have to be empty. Okay, so that is the indexing set for the simple modules. And yeah, without giving you all the details, one thing that we then derived from this were the characters of our representations. And in particular, what we were able to derive is that if you take an irreducible module for this uniform block permutation monoid, which, as I've just described to you, is indexed by a tuple of partitions. So I denote that by lambda vector. If we now restrict this to, so if we restrict from UK to SK, then the multiplicity of the irreducible for the symmetric group is in fact given by this inner product of symmetric functions. So yesterday in this talk, Professor Shimozono gave you an introduction to symmetric functions. So here, for me, S mu is just a Schur function. And when I write S mu bracket SK, I mean the plethysm of the Schur function indexed by lambda K with SK. So what I want to do next is tell you a little bit more about how you actually define these plethysms for the Schur functions. And then I will end with an open problem at the end of the talk. So I want to now relate what I've talked about so far to the plethysm problem, and also define for you what I mean by this S lambda SK. Okay, so let's go back to GLN. So for GLN, we are looking at n by n invertible matrices. And well, if you want to have a representation of GLN, one way to look at it is by a homomorphism from GLN to some other GLM, right? So that would give you a GLN representation. And similarly, if you look at GLM, you can get a GLM representation by looking at a homomorphism from GLM to, let's say, GLR. Once you have that, you can compose two such representations. So I'm going to compose tau with rho. So that will give us a representation from GLN to GLR. And then you can ask what is the character of this composition. And that is also what's called plethism. But now I want to relate this to symmetric functions. So it turns out that the characters of GLN representations can be also described by symmetric functions, in particular the Schur functions. So this is done by the Frobenius map. So suppose that Rn is the space of class functions of GLN, and I'm going to denote by lambda n the ring of symmetric functions of degree n. Then the power sum symmetric functions are defined as follows. So P sub r, where r is an integer, is just the sum of all rth powers of our variables, x1, x2, and so on. And then P indexed by a partition of an integer, is just the product of the P's indexed by the parts. And one way to define the Schur function is as a sum over semi-standard Young tableau, x to the weight of the Young tableau. And the Frobenius characteristic map, well, is a map from the class functions to the ring of symmetric functions, where you map a character to this sum. Okay, where the P mu are precisely the power sum symmetric functions. Yeah, and the Z's are just the sizes of certain centralizers or conjugacy classes. And it turns out that there's an identity on the level of symmetric functions, namely the Schur function can be written as this sum of the power sum symmetric functions. So that tells us that the irreducible character of Sn for GLN is in fact equal to the Schur function. Okay, so now if you think about this composition that we looked at of two GLN representations, I said that the character of that is the plethism. So I'm now going to denote by S lambda bracket S mu just the character of this composition of two such representations. And since that can be again reduced into irreducibles, we know that this plethism of two Schur functions is a positive sum again of Schur functions if we look at this on the level of characters. So one open problem that still exists is what are these numbers? What are these A lambda mu nu? So the open question is find a combinatorial interpretation for these numbers. So in special cases, we were actually able to give certain certain combinatorial interpretations, but in general, this is still an open problem. And one way you might try to understand this problem is as follows. So the Schur functions are given as sum over semi-standard Young tableau. But if you do this plethysm, the combinatorial objects that you're looking at are actually tableau of tableau. So instead of putting a number into each box in your lambda, you're now going to put a tableau inside each box. And well, as I mentioned in my first lecture, right, if you want to find a combinatorial interpretation for some symmetric function as a sum of sure functions, one way you can do that is by trying to find a crystal structure on the combinatorial objects. So in this case, since our combinatorial objects are tableau of tableau, one way to attack this problem would be to try to find a crystal structure on tableau of tableau. And since, well, in Japan, you have a lot of experts on crystal theory, some of you might find this interesting, and I hope some of you will solve this problem. And yeah, this is all I wanted to say today. So thank you very much. And just as a takeaway from this lecture, well, plethysm is a hard problem, but as you try to understand it, you actually you find a lot of other very interesting mathematics, as we did with the representation theory of the uniform block permutation algebra. And well, the topic of this workshop is integrable system and quantum groups. So the other takeaway is that there's a very fruitful interaction between integrable systems, representation theory, and combinatorics. So working out all these interactions helped us to understand everything better. And yeah, here are some photos of my collaborators. Thank you very much.
Do we have any questions? Well, I have one. Has you using the RSK for the well, I was a little confused about multisets because I thought they were just set valued.
Oh, sorry. Yeah, sorry. They are set valued, yes. And then the setting that I was, yes, sorry, I might have said the wrong thing.
Well,
yeah, they were set valued. In the
well,
setting that I was discussing, yes.
Yeah, well, that made me think of two questions. The first is, can you describe basically an ideal of the partition algebra that gives you precisely the irreducible representation analogous to the usual spect modules? And have you looked at trying to generalize that to more arbitrary diagrams?
So you want to find an ideal inside the partition algebra
that you quotient by to give you the spect module, just like, you know, in the classical SN construction?
Yeah, again, this is a very interesting question, but I don't know the answer to your question.
And then my second question is, can you do a semi-standard version of your RSK, and do you know what kind of analog of, I guess, how duality would that entail?
Yeah, so I know that Mike Zabrocki and Rosa Orellana, they actually look at multi-set tableau. And so in their setting, you would look at a semi-standard Young tableau, because you can then repeat you can repeat letters. And yeah, in principle, since RSK, I mean, we are really using the usual RSK algorithm. So as long as you have an ordered alphabet, you can actually apply it. But I think it hasn't been looked at whether that version of an insertion algorithm would have have nice properties with respect to subalgebras or anything like that. So yeah, that I don't think anybody has looked at yet.
All right, thank you. Are there any other questions?
Perhaps questions very much related to what Scrimshaw said, that it seemed to me that finding a cellular basis already the algebra in the section 2, those are cellular, right? So then seems that your approach tells us some candidate for the uniform way of making cellular basis. That's what I imagine. So might be a chance. Sorry, just a comment.
Yeah. Yes. Yeah. That's. Yeah. Thank you for the comment.
Any additional questions? If not, let's thank Anna.
Sorry.
Yeah, go ahead.
May I ask a few questions? Can you hear me?
Yes.
In the your precision problem, so you just write the coefficient a nu lambda mu. Is that a little Richardson coefficient?
No.
No.
No, it's not a Littlewood-Richardson coefficient.
So I'm a little bit confused. So that in the S lambda bracket
It's not a product of two sure functions. It's this composition.
Composition, I see.
So it comes from the composition of two GLN or GLM.
I see.
So it's not the Littlewood-Richardson coefficient. It's some other.
Then so tableau of tableau.
Yes, exactly. So that's how the combinatorial model, that's how it comes about. That yeah, you're actually looking at tableau of tableau.
I see. Thanks.
Any additional questions? If not, let's thank Anna again for her series of lectures.
Yeah, and thank you to the organizers.
And we'll begin at 11 o'clock with the next speaker.